All right, everyone. So for the reading group this week, I've got a really fascinating paper for us to dig into. It's a great example of using generative models to tackle a pretty gnarly problem over in paleoclimatology.
So right off the bat, here's the core intellectual challenge they're tackling. You have these amazing historical archives, right? They talk about things like a great drought. But what does that mean quantitatively? How do you go from these fuzzy qualitative words, which are also super sparse, to a full-blown quantitative climate map? This is, a classic inverse problem. We're trying to infer this continuous physical field, a precipitation map, from just a handful of scattered descriptive data points. It's a really cool, and as you can probably guess, a really, really hard computational problem.
Okay, so here's how we'll walk through it. Pretty standard stuff. We'll start with the problem, dive into their generative AI solution and how they built it, look at the really cool results they got, and then wrap up with what this could mean for the field.
All right, first things first, let's really nail down the problem they're trying to solve here.
So the core issue is this massive data mismatch, right? You've got this incredible treasure trove of historical texts. They give you climate data with amazing resolution, sometimes monthly or even better, but it's all qualitative. It's just words, flood, drought. And as we all know, your standard quantitative models, your regression frameworks, they just choke on this kind of stuff. It's sparse, it's non-numeric, it's just a completely different beast. Okay, so this brings us to the key insight. And this is where I think they make a really clever conceptual leap that kind of flips the whole problem on its head. Yeah, so the big idea is this. They completely invert the logic. Instead of the old way, which was trying to go from a known climate state to predicting where a drought might be recorded, they do the reverse. They ask the AI, given that we know a drought was recorded here and a flood was recorded there, what is the most likely, physically plausible climate map that could have existed to cause those events? It's a generative approach, working backwards from the sparse evidence.
And this diagram just lays it all out perfectly. On the left, you see the old way of doing things. But check out their pipeline on the right. They start with these big climate model simulations to basically create a synthetic universe of weather. They use that to train a diffusion model. Then, and this is the key part, they feed the real historical archives into this trained model. What comes out? A full quantitative climate reconstruction. And once you have that, oh man, you can do all sorts of cool downstream science, analyzing extreme events, finding climate patterns, stuff that was totally impossible before.
Okay, let's get into the weeds a bit. Time to look at the method, the technical core of this thing. This is the part that I think will be most interesting for us.
So why a diffusion model? Well, their choice here was anything but random. As many of you in this room know, diffusion models are fantastic for these kinds of inverse problems. Their whole deal is denoising from a random state, which makes them inherently robust to messy, sparse, incomplete inputs, which is exactly what we have here. Plus, and this is critical for any scientific application, they're generative. You don't just get one answer, you get a whole ensemble of possible climate fields. That's absolutely perfect for quantifying your uncertainty.
Now, this next part, I think, is the most clever bit of the whole paper. They have a classic no ground truths problem, right? There's no historical data set that pairs a scribe wrote about a flood with an actual quantitative precipitation map from the year 1500. So what do? They make one. They fire up a massive climate model, generate over 1,700 years of synthetic climate data, and then from that simulation, they observe synthetic extreme events, making sure the data looks just as sparse as the real historical records. This gives them a massive training set of event map, precipitation map pairs. They literally built a synthetic reality to teach the AI the physics of how weather works.
In digging a little deeper into the architecture, there are two really neat choices they made that are worth pointing out. First, they use a 3D UNet backbone. This is smart because it lets the model think about space and time together, jointly, which is obviously crucial for weather patterns. The second thing, and I thought this was just elegant, is what they call a periodic conditioning prompt. This is a clever way to handle the fact that the historical Chinese calendar is lunisolar, not Gregorian. It solves out alignment headache and doubles as a really effective data augmentation technique. Super slick.
So, does it actually work? Well, yeah, it really does. They tested it on a held-out chunk of their synthetic data, and the skill scores look pretty solid. You can see the R-squared is 0.65 for annual data, so it's explaining a good chunk of the variance. The CE, which is a tougher metric, is up at 0.70. But the one I really want you to look at is the SSR, the spread skill ratio. It's hovering right around 1, and that's fantastic news. It tells us the model has a good handle on its own uncertainty. It's not being overconfident or underconfident, which for a scientific model is absolutely essential.
Okay, so we've established the method is solid.
Now for the fun part. Let's look at the payoff, the actual new science they were able to pull out of these old texts.
Take a look at this. This is the infamous Wye River flood of 1593. Before, all we had were written accounts saying it was a great flood. Now, for the very first time, we can actually see it. We have a quantitative map, we can see precisely where the core of the event was, and we can quantify it. That's precipitation more than 3 standard deviations above normal. This is turning history into hard data. And here's another one, a really famous one from history, the drought in 1640 that helped bring down the Ming Dynasty. The model doesn't just say it was dry, it paints a picture of the devastating scale of this thing. Look at that deep red covering northern China. That's more than 2 standard deviations below normal rainfall. You can even see the sharp southern edge to the drought, right around the Wye River. That's incredible detail.
And this is where the model really starts to show its power to uncover things we didn't know. The Guangzhou drought of 1877. The texts just talk about a widespread drought, but the model reveals this really interesting heterogeneous pattern. It was much worse in the west than it was in the east. See that west-heavy, east-light structure? That's a subtle spatial pattern that you'd completely miss just by reading the chronicles. The AI is finding structure in the data that wasn't obvious to human readers.
Now, this slide is super important for validation. What we're looking at are the dominant modes of climate variability. You can think of them as the EOFs, or the principal components of the data. On the right, that's what you get if you just use the raw, sparse historical records. It's messy, kind of noisy. But on the left, that's from the model's full reconstruction. Look how much cleaner and more physically coherent those patterns are. This is the smoking gun, really. It shows the model isn't just playing connect the dots, it's actively synthesizing the sparse historical data with the underlying climate physics it learned from the simulation. It's producing something new and more meaningful. Okay, this is seriously impressive. This is a huge out-of-sample test. What they did was look at the correlation between their reconstruction and ENSO, El Niño, which is, the biggest driver of climate variability on the planet. Panel F shows that correlation over their entire 544-year period. And what does it find? It perfectly recovers this classic dipole pattern, wetter in the south, drier in the north, that we know from modern instrumental data, which is what you see in Panel G. The fact that it pulled this out of the data is a massive vote of confidence. It learned a real-world, global-scale climate connection. But here's where it gets really powerful. Because they have over 500 years of data, they can see how these connections change over time. Just look at the difference between the 17th century on the left and the 19th century on the right. The ENSO connection isn't static. Its strength and its spatial pattern clearly shift on a century-long timescale. This is the kind of long-term, low-frequency variability that is completely invisible to us when we only have our short, modern instrumental records. This is brand new climate science. So, let's zoom out. What are the broader implications of all this? Because it really goes way beyond just this one dataset. You can just see the avenues for future work branching out from here. I mean, the low-hanging fruit is obvious. Use a modern LLM to do way more sophisticated feature extraction from the texts, right? Not just flood or drought, but maybe intensity, duration. You could, of course, take this whole framework and apply it to other historical archives around the globe. But the really big idea for us, I think, is this blueprint for multimodal data fusion. Imagine a unified AI framework that can ingest text, tree ring data, ice cores all at once. This really feels like the beginning of a whole new paradigm, something like physics-informed digital humanities. And that really leaves us with a pretty provocative question to chew on. This paper was about climate, but think about this general approach, using generative models trained on realistic simulations to decode sparse and qualitative historical records. What about economic history, or the spread of diseases, or the dynamics of historical conflicts? It makes you wonder, right? What other deep knowledge is just sitting there, locked away in our libraries and archives, basically waiting for one of us to build the right model to finally read it?